So the latest IPCC report on climate change reckons that a warming of about 3.5 degrees to 4.8 degrees by 2080 would expose around 400,000 more people in Europe to river flooding, and about 5.5 million more per year to coastal flooding. In the UK specifically, the annual cost of flood damage could increase by around 15 times more in 2080 than it is now. So with this in mind, it's important that we continue to develop cost-effective and easy flood detection tools. With these flood detection tools that I've developed, they use a method called satellite remote sensing, which uses satellite data to look at the Earth's surface, and from this we can detect floods using this images. So we start with dividing the UK into multiple regions. And for each region we divide the UK into, we try and retrieve optical images from Copernicus's Sentinel-2 satellite. You see an example here, a flood, not too far from Warwick actually. And you see that we have the grey areas show where flood has happened due to the banks of a river overflowing. So to actually identify these water pixels better, we use an index called NDWI, which stands for the Normalized Difference Water Index. And the difference between these two optical bands, B3 referring to green light and BAA referring to shortwave infrared light. And as you can see, if we look at this optical image in NDWI, the surface water present in this optical image appears much more whiter and brighter compared to the land and vegetation around it. And so with images like this, if we subtract two different flood images, we can compare the two and find which part of the image contains flooded water. And we do this basically over multiple years and multiple regions across England. So a visual demonstration of that is at the bottom. We have our flood image, white pixels, show the flood water, and then our pre-flood image is the image before the flood. As you can see, that the only surface water present here is the river. Subtracted them gives you a darker pixelated image where the flood water is present. With those darker pixels, we can then extract them and threshold them, and we end up with a blue flood mask. So with England, we split into 65 regions. Each region has about 774 kilometres squared. And between the years 2019 and 2021, we detected 162 separate flooding events in England. So here's some examples. We have the pre-flood images. As you can see, that any water present before the flood is shown in blue. And so in the winter of 2019, the algorithm detected these specific flooding events. As you can see, the rivers have burst its banks and the water has flooded low-lying crops and fields. Other examples here include cloud, which isn't a problem. Subtracting flood and pre-flood images still allows us to find all these floods. So once we have a collection of flood data, we want to make sure we know exactly which pixels in the images are floods and non-floods, so we can provide an accurate map of a flood to give to emergency services and local authorities to know the exact location and extent of a flood. And so this assigning of a pixel to be flood or non-flood pixel is called classification. We give it either a value of 1 or 0. So how do we determine whether a pixel is a flood pixel or non-flood pixel? Well, we use further indices, including the water index I mentioned earlier. We use NDVI, which is Normalized Difference Vegetation Index, which is good at observing vegetation cover across the land, and VI is the Brightness Index, which is how bright the optical image is. So we calculate these indices for each individual pixel, and basically for a lot of thresholding statistics, we end up with a final classified flood image. As you can see, the blue pixels are the flooded pixels that we've accurately classified. So we do this for 162 floods, and we store all this data as training data. So this training data leads us on to the artificial intelligence. So the AI is a machine learning model that uses a random forest classifier. The AI basically takes in the flood and pre-flood optical images, including the radar images. It trains, we train the AI using the optical indices we saw before, NDVR and so on, along with some other radar data. So we teach the AI using our previous classifications, and it learns from that how to automatically detect those floods by itself without any human intervention. And the output is an automatically detected and classified flood. So example here on the left is a flood in Worcester in England, and on the right is our accurately classified flood mask. And we classify 50 images in the machine learning model, and average accuracy of about 98.9%, and high average precision scores with those pixels as well. So finally, what use are these detection algorithms in real life? Well, a simple and cost-effective detection algorithm will be good in remote regions where flood surveillance is less common, and along with an accurate flood classification will make an effective overall tool for emergency services to use. And the final next steps are to use the data worldwide to collect more training data, and to finally teach the AI model to classify these flood images using radar data only, which is more effective than optical images as there's no cloud. And I think that's the end of the presentation. Thank you for watching.
Thank you, Angie. That